What I'm going to show you next is a very large number of experiments, which I'm going to do without a computer. So this time, I'm going to look at 12 steps, which are the beads bouncing on these pins, okay? And I got 3,000 beads at the bottom here. So we're going to do a sequence of 12 flips 3,000 times, and we'll see what we get. I think you can see we're getting a normal distribution. In fact, there's a reference line there. I'm going to do it again. There we go. Okay, so we have here a normal distribution, and because my my hand was slightly tilted, we get a slightly shifted normal distribution, but I'll do it one more time. I'll try and keep it really horizontal this time around. Okay, so we have a normal distribution. This time, in our normal distribution, we have not had to use a computer. So I'm going to share my screen one more time and look at this experiment in more detail. And it turns out that that involves an integral, but it involves an integral that is very hard to do, and we'll find a trick to do. It's an integral that everybody should know how to do, because it's an integral of something that you're going to use if you use mathematics pretty much all your life. And this is the fun bit, your teachers might not know how to do that integral, because quite a lot of people don't know how to do it, and it's not actually that difficult if you do it the right way. So that device I just showed you is called a Galton board. Okay, so that's called a Galton board. It's named after a scientist who's a little bit controversial. And if you want to find your own version of it on the web, if you browse Maths is Fun Galton board, okay, Maths is Fun Galton board, you'll find an app which is free from this website called Maths is Fun, even though you already knew that. And this website will give you this particular app that I just taken a snapshot of it, and it allows you to set the number of pins, set the probability of going left or right each pin, set the speed, and you can create as many bouncing balls as you want. Now, interestingly enough, these balls are going to just go right and left. They will not bounce like the ones that I was showing you earlier. So this is an exact and correct replication of the Toyn-Costing experiment. This is actually not, it turns out. This is actually because the beads bounce off the pins. So this is actually a simulation of a gas. Okay, the bouncing of the beads on the pins simulates the speed of the molecules in a gas, and that is a reflection of the temperature of the gas. So a high temperature gas corresponds to beads going down very fast and bouncing a long way, and a low temperature gas corresponds to them coming down very slowly. And at close to zero temperature, you will get something very like this exact experiment that you see on the screen. Right? And for those of you who are doing the binomial distribution at school, well, what this is showing is that if you take a binomial distribution with many categories, it is well approximated by the normal distribution. Okay? Now, the normal distribution needs to have certain characteristics. It needs to be symmetrical about the mean. You can see here, it's roughly the same right and left if you have an unbiased coin or unbiased ball on a pin. It needs to extend to infinity, not in the case of binomial distributions, but for the real continuous distribution, it needs to extend to infinity. And it needs to have a given width that controls the standard deviation. It turns out that the normal distribution has got some amazingly optimal properties on something called entropies. They absolutely is a magical thing. And all of that was derived by this gentleman who was born in the 18th century and died in the 19th century, called Carl Friedrich Gauss. And that little beta looking symbol at the end is German for SS, Gauss. We normally write with GSS. And the formula is a formula that you will have learned at school, I'm sure, and it's a formula that you learn at university. And in this formula, you have, let's not chop up Gauss's head because that would not be very kind. So you have the mean value over there called mu, and because the function only depends on the distance between x and mu, it's symmetrical, because whether x is to the left or to the right of mu, it's the same difference when you square it. And it's got the width determined by sigma, And that is the correct formula for it. Okay, it's a major triumph for mathematics to show that that particular bell-shaped distribution has this exact formula. Okay, and that's something called the central limit theory that tells you that if you look at the mean value of any number of experiments, if there's a large enough number, the mean value will have that distribution, which is why even that gas simulation gives you this distribution very accurately. But there's a problem, and that's where the integral comes in. The problem is that, as we know, the area under this curve needs to be 1. So the area of fx, I'll try and stay on the window this time, when x goes from minus infinity to plus infinity, that has to be 1. And it isn't. Okay? So what we're going to do is we're going to say that fx is we're going to write it as equal to that same expression divided by some number a called the normalization constant. Okay, and I make sure that I've erased it approximate. And a is going to be the integral from minus infinity to plus infinity of the function f, or as it originally was. I've done it again, gone off the screen. I'll have to definitely stop that. Now, this function, which is the area of this bell-shaped curve, doesn't depend on whether the curve is located to the left or the right. It only depends on its shape. So you can position the mean of it any way you like. I'm going to position it at 0. So to do that, using my tablet, it's very easy. I just set this mu to 0. Okay. So now I have an integral that is fairly easy to do. Now, notice that this integral, I should have completed my integral by writing d of x, of course. I'm going to write it out now. Go on. Yeah, d of x. Now there's a problem. Notice that if you're trying to do that integral, you need to find something that differentiates to it. But if you differentiate this complex expression, the exponential of e to the minus sigma square of x squared over sigma square, and what I've done is I've set mu equal to 0. That's why it doesn't appear there. Differentiate, that's my tilde there, my dash. Then what you get is minus a half. When you differentiate, you first differentiate what's inside the argument. That's a chain rule. So you get minus a half times twice x over sigma square, which is this. And because you're differentiating the exponential as well, the exponential gives back itself. So what you get is minus x over sigma square, it minus a half times x squared over sigma square. Right. And the problem you now have is this little character, this x. Now it's a big problem because it's missing from the top, from the integrand. And unless you have x in the integrand, you cannot do the integral. So it's essentially an impossible integral that we're going to try and do. And in doing it, we're going to use this property. Okay? So we now have an impossible integral. So what we're going to do now is try and do that impossible integral. How are we going to do it? Well, we're going to do something that on the face of it looks a little bit ridiculous. We're going to square it. So remember that a is that integral, right? So I'm going to square it. So I'm going to say, well, a squared is this integral from minus infinity to infinity e to the minus, and I'm going to write it like this, just for the sake, for brevity, right, to begin with. And I'm going to square it, but when I square it, I'm going to use a different variable. I'm going to call it y. And you'll see why in a moment if you don't mind the pun. Okay? Now, instead of having one difficult integral, I've got two difficult integrals multiplied together. So why on earth would I want to do that? Well, there's a really good reason why you want to do that. And that reason is that now I'm no longer doing an integral over the real line. I'm doing it over a plane. Okay, so how does that help you? I hear you ask. Well, you should be asking. Well, it helps you because on a plane, I can use a different set of coordinates, right? So on this plane, I can use not Cartesian coordinates after Descartes, which are the ones x and y, these things. I can use polar coordinates. In polar coordinates, I determine a point not by the value of x and y, as we normally would do, but by the distance from the center and by the angle to the horizontal. Okay? Now that's quite handy because there's this nifty trick I'm going to show you now. I'm going to do it in green, which is the following. The element of integration in an area, dx, dy, which corresponds to a little bit of space that we're going to integrate over, now is determined by polar coordinates. So instead of being rectangular, it looks like an arc. Okay? And the area of this rectangle is dx dy, because dx is, if you want, dx is the size of the bottom of that area, and dy is the size of its height. But in the case of the polar coordinates, it's much more fun than that, because the area is given by the delta r, which is the increase in radius, obvious, but that's the bit now that's going to save us, this bit on the side here, because that is an arc. And if you remember from your geometry, the size of an arc, a distance r away from the center, is r d theta. It's not just d theta, it's r d theta. Okay, so now that's going to be proper handy, because now I can rewrite my integral, and my integral, which involved dx and dy, now is written as the a square is now the integral over r from 0 to infinity, because the radius from a plane, if you want to cover the whole plane, you go from 0 to infinity, and the integral over theta going from 0 to 2 pi, because you have your radius going from 0 to infinity over the whole of the plane. And the argument is now e to the minus x squared plus y squared over twice sigma squared. And I'm going to show you why that is so handy, because you know from Pythagoras that x squared plus y squared is equal to r squared. This might even look like an r if I'm a little bit careful, which means that that integral can now be written in the magical form, which is 0 to infinity dr, 0 to 2 pi d theta, e to the minus r squared over twice sigma squared, with one change to my equation. And that change is that, if you remember, the element of area is r d theta, not just d theta, okay? Which means that the element of the little rectangle dependent on theta is now r d theta, and this has got an r d theta over here, and that's what's going to help us, because it's going to provide that value that was missing earlier on. So to show how this works, so coming back to this integral, a squared is therefore going to be, well, The first thing is I can do the theta integral because there's no dependence on theta anywhere. None of this depends on theta. It only depends on r. So the theta integral just gives us 2 pi. And the r integral gives us the integral from 0 to infinity of r, which is that r over here, e to the minus r squared over twice sigma squared dr. Okay, and that's very handy because this is the integral that we can do because you have this drop-down term r that allows us to integrate the e to the minus r squared. Okay, and when you do this, what you get is your 2 pi, and it turns out that the integral of all of that in the integrand is e to the minus r squared over twice sigma squared. I'm going to go back up and show you. So I'm going to go back up and show you why that is. It's because of that property that the derivative of e to the minus x squared over twice sigma squared is minus x all of that, minus x over sigma squared all of that. Therefore, the integral of e to the minus half x squared sigma squared multiplied by x, which is what we now have, but with an r instead of an x. So the integral of x e to the minus all of that is equal to minus sigma squared times that lot. So that's what we're going to write now. Put the minus sigma squared there. And it's done between 0 and pi by 2, 0 and 2 pi, because that was the integral that we're doing. Sorry, 0 and infinity, because that is the integral of r. Okay, and if you take this expression and work it out, you get 2 pi sigma squared. Then you have, I'm going to put the minus sign inside the integral. So I'm going to have minus e to the minus r squared over twice sigma squared. When r is infinity, it gives you infinity squared. And then minus e to the minus 0 squared over twice sigma squared. And this is infinity. Okay. And e to the minus infinity just gives you 0, because the exponential of a negative very large number is 0. These two signs add up to a minus, because we know that 2 is up to a plus, because 2 minuses make a plus. We know that any power of 0 is 1, so e to the 0, e to the minus 0 square over something, well, e to the 0 is 1, so that gives you 1. And therefore, the total integral just gives you twice pi sigma square, which means that the value of a is sigma root of 2 pi, which is the square root of 2 pi sigma square, with the consequence that the value of the function, when you put the value of a back into the denominator, is as written on the screen. Okay, so just to recap very briefly, we started with an expression that needed normalizing. The normalization is the integral of the top, because when you integrate f with a in place, you integrate the top and you divide by a, but a is the same as the integral of the top, so you get 1. So you get the requirement for the probability distribution, the probability mass function called f, to integrate to 1. So to do that, you need to calculate this impossible integral, where you can set mu to 0 as you wish. But you realize that when you want to integrate an exponential, you have the problem that the derivative of an exponential with x squared in it is going to require a value of x multiplying the exponential. And we haven't got that value of x in the integral above. So we resort to a trick. We square the integral by having it multiplied by itself in the direction x and in the direction of y. That enables us to change from Cartesian coordinates to polar coordinates. And in polar coordinates, we know that the area element corresponding to theta has a factor of r. That's because this arc element here has a length that depends on how far you are from the origin. So the area element is the change in r multiplied by r times the change in theta. And that comes to our salvation here, because x squared and y squared is the length of the radius square. Therefore, that integral can be written in this form, which is an integral over r and over theta. The theta integral is trivial because there's no dependence on theta anywhere, right? So we end up with an integral over r, which has the element of r multiplying e to the minus r squared that we needed in order to be able to do it. And when we do it, we get just the exponential. That's because the derivative of this exponential is the exponential times the derivative of the argument by the chain rule, and that gives you our twice r with a minus sign, which is over here, and the value of 2 cancels out with that value of 2, and you put a sigma to compensate. So all of this, believe me, adds up correctly. This integral has now been done. The impossible integral, when you square it, has been turned into a possible integral through this trick of converting from Cartesian xy coordinates to polar r theta coordinates. So the integral corresponds now to this exponential term that you must find between the limits of 0 and infinity, because that's the limits for the radius. At infinity, you have e to the minus infinity, and e to the minus infinity is 0. So that drops down. So that term disappears because it becomes 0. This term at the lower limit is e to the minus 0, and 0, up anything to the power of 0 is 1. So that gives you 1, and therefore your whole integral just becomes 2 pi sigma square. The square root of that, which is a, because remember this is the calculation of a squared because you got the integral twice over. So that gives you a equals to the square root of 2 pi sigma square, which is the square root of 2 pi times, well, the square root of sigma square is sigma, so I pull it out to avoid confusion. And we write it out like this. So this is the formula that you will see in every statistics book, in many mathematics books. It's a formula that you'll be using in the normal distribution at school, you'll be using at university, you'll be using it if you work as a mathematician or as a statistician for most of your lives, but you now be able to say to anybody, including your teachers, I know how to calculate that number. And I bet you quite a lot of people don't.